everyone, and welcome to Getting Indefinitely Rich While Going Broke. Our presenter today is Dan Swenson from Black Hill State University. If you have any questions for the presenter during the session, please feel free to enter those into the chat at the bottom of the Zoom room screen, and we will be sure to address those at the end of the talk. And on that note, I'll go ahead and hand it over to our presenter.
Well, thank you, Sydney, and thank you very much to everybody joining us today. Well, let's get rich. How are you going to get rich? Slot machines, obviously. So we have today infinitely many slot machines labeled 1, 2, 3. There are countably many infinitely slot machines. And for each penny that you insert into machine N, it returns either 0 pennies or n+1 pennies. n+1 pennies with probability 1 over n, and otherwise 0 pennies with probability 1 minus 1 over n. So they're complementary probabilities. And here's a chart of it. One thing about this machine 1, you can see is it's a guaranteed win. So you put a penny into machine 1, it guarantees you get 2 pennies out. So your expected value is definitely guaranteed to be 2, which is better than 1. So obviously this is a get rich scheme. But even actually the other machines are really not too bad also, because like look at machine 2, for every penny you put in, you expect to get 3 halves of a penny out, 1.5 pennies out. Or even machine N, the nth machine, even the nth machine gives you a little bit of an edge, slightly more than 1 penny out for every 1 penny you put in. Here's a picture of these machines. I did not draw all of them. Actually, I didn't draw any of these. I got this picture online. But anyway, you can see there's a progression from one. We'll move from one machine to the next. And the rules are we have to play every machine. We have to play the machines in order. So 1, 2, 3, 4, etc. And you know what? Go big, go home. Go big or go home. We're going to put all of our pennies into every machine. And that means that we'll get, if you put in multiple pennies, well, you get to play that machine multiple times, right? Pull the lever. So here's an example. We start out with 1 penny. That's that little gold circle. We put it into machine 1. And well, machine 1, if you remember, that's guaranteed to give you 2 pennies out. Machine 1 is the guaranteed winner. So we get, put 1 penny in, we get 2 pennies out. But now those pennies both go into machine 2. And I mean, I just put them in parallel here so you can kind of see more what's going on. Each one of them gives us 1 play on machine 2. All right, so let's say what happens in machine 2. Well, let's see, I guess our first play, unfortunately, is a loser. We don't get anything back from that one. But our second play is a winner. And remember, machine 2 gives us 3 coins. In general, machine N, if you win, gives you n+1 coins. So machine 1, if you win, well, you're guaranteed to win, gives you 2 coins. Machine 2, if you win, guaranteed to give you 3 coins. So what do we do with those 3 coins? Well, they all go into machine 3. And machine 3, well, let's see, our first play is a loser. And our second play is a loser. And our third play is unfortunately also a loser. And so we are done. And then we feel sad. All right, so here's some questions that we might have for this these slot machines, like how much money are you going to have? Or a more mathematical way to state that is, after machine K, what is your expected number of pennies? Of course, that's a random chance is going to come into this, but we could talk about the expected value. And well, we just saw how you could go broke. How long does it take until you go broke? Or wait, maybe you don't go broke. Do you go broke? I don't know. Let's find out. So a mathematical way to ask that question is, after machine K, what is your probability of having exactly 0 pennies? And you can also ask, okay, well, what happens to that probability as K goes to infinity? You know, is the limit 1? Does that limit even exist? I don't know. So these are mathematical questions that we could ask here. And that last question I think we can answer. Let's let BK be the probability. B stands for broke. So the probability of being broke after machine K is BK. And then the proposition is that, in fact, that limit exists as K goes to infinity. And the proof is the monotone convergence theorem. Of course, BK is always bounded above by 1 because it's a probability. And then also that sequence is monotone increasing. Why is that? Well, the idea is if you're broke after machine 3, then you're also broke after machine 4 and after every machine in the future. Why? Because you can't get any more money if you can't play, and you can't play if you don't have any money. So that broke probability just increases and increases towards some limit by the monotone convergence theorem. All right, so here I wanted to introduce a kind of mathematical gadget. It's called a generating function. So remember, machine n either gives you 0 pennies or n plus 1 pennies, and there's these probabilities attached to those two outcomes. Well, we can encode those numbers into a polynomial. So if you look at both this qn, this is a polynomial. It has two terms in it. Both of them have an x raised to some power. We have x to the n plus 1, and we have x to the 0. That power is the outcome of that event. So either you get n plus 1 pennies coming out, or you get 0 pennies coming out. That's the exponents on these x's. And then what are the coefficients? The coefficients are attached are the probability of those events. So what's your probability of getting n plus 1 coins? It's 1 over n. What's your probability of getting 0 coins? Well, it's 1 minus that, because of course the probabilities add up to 1, and you could write that polynomial however you want. That's what this polynomial is doing. And that encoding of that information is called a probability generating function, or PGF. So I don't know, maybe you'll look here, any questions about how we're doing this encoding. The exponent is the outcome, and the coefficient is the probability of that outcome. Here's some of these probability generating functions for the various machines we have. First of all, machine 1, remember, is a guaranteed winner. You're guaranteed to get 2 pennies out. So 2 pennies is 2 is in the exponent, and the probability 1 is telling you there's a guarantee of getting 2 pennies out. Machine 2, well, you have a 1/2 chance of getting 3 pennies out. And then there's also a 1/2 chance of, well, that's an x to the 0. So there's a 1/2 chance of getting 0 pennies out. In general, these are the QNs. And I also took the liberty of taking the derivative of these functions. Here they are. And in this right-hand column way over here, I plugged in x equals 1 into those derivatives. And we get these numbers 2, 3/2, 4/3, 5/4. And in general, just a little bit more than 1, n plus 1 over n. And if you remember, we actually saw these numbers before. Those were the expected value of the outcome for each of those machines. So plug in x equals 1 into the derivative, and you get the expected outcome, the expected value of that outcome. Also, what if you plug in x equals 1 into the original function? Well, it turns out you just get 1. You can see that down here at the bottom. If I plug in x equals 1, well, it would be 1 to the n plus 1, and then plus n, then minus 1. So that's just n on top and n on the bottom, and you get 1 coming out. So q prime is the of 1 is the expected value, and q of 1 is just 1. And that's not really a surprise or a coincidence. Actually, that will always happen with these probability generating functions. So in general, if you had a probability generating function that looked like this, so A0 is the probability of getting 0, A1 is the probability of getting 1, A2 is the probability of getting an outcome of 2, etc. Well, if you plug in x equals 1, you just get the sum of those probabilities. And the probabilities are supposed to add up to 1, because that's kind of fundamental to what it means to be a random variable, I guess. So the probabilities have to add up to 1. What if you plugged in, took the derivative? Well, then these exponents would come down in front. So it would be like a 2a2 times x, or a 3a3 x to the 2. And if you plug in 1 into that, well, then the x's basically just go away. And so you're left with this summation with the 0 and the 1 and the 2 on the front. And what is that? 0 times the probability of getting 0, 1 times the probability of getting 1, 2 times the probability of getting 2. That's the expected value formula. Okay, so that's kind of always works. So now what we want to know is, what is our probability generating function for, well, not just one machine at a time, but after the first k machines? Let's see, after 0 machines, well, we haven't done anything, and we know we start with 1 coin. So we have x to the 1 with a probability 1 guaranteed. And after x equals, after machine 2, well, sorry, after 1 machine, machine 1 is the guaranteed winner. So we still have a guaranteed probability of 1 of having a x squared, so that means 2 coins. If you do a little bit of math, you can figure out what are the possible outcomes after machine 2. Remember, machine 2 is the one that gives you either 0 or 3 coins, and we actually saw both of those possibilities come out. And so it's going to give you 3 coins at a time. So, and we know we're going to plug in 2 coins. So we might get 6 coins, we might have 3 coins, we might have 0 coins at the end. And these are, it turns out these are the probabilities. What about P3? It's starting to get harder. But I mean, if you know what P2 does, P2 is your states, the possible states, or how much money you might have after machine 2, before machine 3. And Q3 is telling you what machine 3 does. So it seems like P2 and Q3 together have enough information to tell me what are the possible outcomes after machine 3. But what is that? How do we do that calculation? Well, here's an idea. Each factor of x stands for a coin. Like if you had x to the 6, that means you'd have 6 coins, or x to the 3rd would mean 3 coins. But now we're taking each coin and plugging it into this machine. And that means that each coin is sort of going to represent a random variable with a possible range of outcomes, or actually, again, in our case, 2 possible outcomes. And we're going to treat the coin as a superposition of what it might result in. So if you've done like quantum mechanics or something, you've heard of Schrodinger's cat, and that's like a superposition of a cat that's 50% a live cat and 50% a deceased cat, and it's sort of, they call it a superposition of those 2 possibilities. And so what we're going to do, we're going to take every x and replace it by its superposition, which is, well, there's a chance that it'll turn into nothing, and there's a chance that it'll turn into n+1 coins, and there's the probabilities are attached. That's exactly our friend Qn. But now wait a second. Pn-1, we're replacing the x's with something. And what that means is we're applying that function at this. Or if you're taking one function of another function of x, well, they call that composition of functions. So it turns out the idea would be we would want to compose our Pn-1 with our Qn, and actually that's not just an idea, it's a theorem that this actually works amazingly. So you just replace all the x's by what they might turn into. So here's what we get. You know, you kind of build this like chain of compositions to give you each one of these PNs. But now I'd like to stop here, because if you look at this composition a little bit, you'll notice something kind of funny, which is, you know, think about how we would do this. Well, we're going to go from machine 1 first, and then machine 2, and then machine 3, and then machine 4. But how is this composition being done? When we write composition of functions, we write it right to left. So if you were going to apply this composition, you'd do Q4 of x, and then Q3 of that, and Q2 of that, and Q1 of that. So Q1, I mean, machine 1 is the first machine we do, but somehow Q1 ends up being the last function applied in this composition. This is sometimes, so I mean, the composition is actually going backwards from what you would maybe expect chronologically. And when we compose functions in the reverse order, sometimes people call that contravariance, I guess, but that's just a fancy word for compositions going backwards from what you'd expect, I guess. So here's our P1, P2, P3. By the way, yeah, this is how we're going to get P3. This is also a way to get P2, because notice this was our function, P2, and it does satisfy this property of being exactly P1, the squaring function, applied at Q2. Okay, so I mean, I guess it's sort of working. By the way, if you're interested in the expected value, well, the expected value is just what you get if you take the derivative and plug in 1. But taking the derivative, well, our function is a composition, so derivative means chain rule, and then we'll plug in 1. At one point you have to do Qn of 1, but Qn of 1 is 1 because of some function, some formula we already did. And so basically you end up just kind of multiplying these fractions together, and they all sort of end up somehow canceling out, and we just get n plus 1. So the expected value after n coins, I know that went pretty fast, but you can take my word for it. After machine n, your expected number of pennies is exactly n plus 1. And that's great, because that means that our expected value is going to infinity. As n goes, as we go through more and more and more of the machines, our expected value is going to infinity. We are getting infinitely wealthy, which is great. And also, we answered a question in mathematics, which is also equally great as being infinitely wealthy. So the other question was, what's your probability of being broke? And well, let's see. Probability of being broke, that would mean that we have 0 coins. And the probability is the coefficient. So we weren't looking for the coefficient on x to the 0. Coefficient on x to the 0 is the constant coefficient, though, right? That's what it means. So how do you get the constant coefficient? Plug in x equals 0, and you get the constant coefficient left out. That's all that's left. And it is a theorem that the probability of going broke as n goes to infinity approaches the number 1. This is left as an exercise. I would characterize it as a hard exercise. At least I thought it was hard. Maybe somebody can tell me why this is easy. That would be great, actually. Just hit me up in the comments or whatever to say, listen, Dan, that's really easy, obviously. But I wanted to skip ahead. Dr. Dominic Clevey did mention the St. Petersburg problem. And if you're, in the few minutes that we have left, if you're familiar with the St. Petersburg problem, yeah, you just keep flipping a coin until you get the tails. And then what's your payout? Well, it's 2 to the number of heads that you got. So either 2 to the 0 or 2 to the 1 or 2 to the 2. So your payouts are either 1, 2, 4, 8, etc. And we can model this using the kind of a similar tactic. Maybe this is best shown with a picture here. So what I have in mind here is actually 2 types of coins. One type of coin that's like your bank, that's how much you're going to win, guaranteed to win is your bank. And the other coin up there in the yellow, that's your flipping coin. If you flip heads, well, your guarantee doubles and you get to flip again. Flip heads again, well, you double your bank and you retain your flipping coin. Hit heads again, you double your bank again, and you retain your flipping coin. But if you hit tails, well, then you're done and you just are left with your bank. Well, you can do this. We have 2 kinds of coins. We need 2 variables, x and y, but this still is the composition. And what's this inside? Well, what's the P0? That's what you start with. You start with 1 flipping coin and 1 banked coin because your guaranteed winnings is always at least 1. And that's guaranteed what you start with. The only hard thing is what's this QN inside? You have to figure out what's going to happen to all of the flipping coins and what's going to happen to all of the bank coins. Well, the bank coins just stay as they are. So every banked coin just remains a banked coin. So the Y's just stay Y's. But your X might turn into nothing, or it might turn into retain that X plus get a bunch of banked coins as well. And if you plug in those numbers, you can see exactly what these outcomes are, what the probabilities are. If you know about the St. Petersburg paradox, these are the numbers that you'd probably expect to see. After 4 coins, there's a 1 in 16 chance that you still are flipping. And the y, the exponent on y is telling you what your bank was. Quick comparison. So yeah, as Dominic put in the comments, your payout is always finite, but somehow your expected winnings are infinity, which is really weird. But if you think that's weird, then I think the infinite slot machines problem is also at least equally weird, because you're guaranteed to go broke with probability 1, and yet your expected winnings go to infinity. So with that, I think I'll just say thank you very much. It's been a pleasure talking with you guys, and thank you very much for your comments in the chat. I appreciate it.
Thank you so much, Dan. We appreciate it. It seems that we are right out of time. So thank you again, Dan, for all of the valuable information you shared with us today, as everyone is mentioning in the comment section. If you have any remaining questions, feel free to stop by the Hawks virtual booth to speak with a member of our Hawks team, or questions for Dan. I'm sure you can always put them in the chat and he'd be happy to respond through the chat as well. But the next session will begin right at 3 p.m. So just in a few minutes here, you can view the chat for the session meeting room links or access the conference website for a complete list of sessions and their descriptions. While accessing the conference website, don't forget to swing by the virtual booth to say hello to the Hawks team. And here you can also view a quick 5-minute demonstration and be entered in to win a $50 Amazon gift card. I'm going to put that in there now, and we will see everyone at the next session.
Great. Thank you, guys.
Bye-bye. Thanks. By the way, I have a question for you.
Yeah, what's up?
Yeah, it kind of reminds me of something I read in the book of Optimal Stopping by, I don't know if you're familiar with that.
I'm not familiar with that book. I mean, if you want to send
Anyway,
me a link or the name and author, I'd be happy to check it out.
Yeah, I just mentioned that they mentioned the problem like yours that you,
Mhm.
so it really boils down to where to stop, right? So when do you want to stop gambling? And so that's an example of that. There doesn't exist a point of stopping. So
Yeah, that's right.
Yeah.
I mean, the thing about actually the St. Petersburg problem and this also slot machines thing is that at every point you have a positive expectation. It's in expectation you would expect to get more money by playing another round.
Right.
But also it turns out that if you always do that, that's a terrible strategy. So
yeah. Check out the book. It's called Great Expectations.
Great Expectations. Well, I've heard of that book, but
yeah, but it's by Chow, Robbins, and Zygmunt. I need to look. It's by 3 authors. It's an old book. It's a classic from the 1960s. So
okay.
It's called Great Expectations: The Theory of Optimal Stopping.
Okay, fantastic. Yeah, definitely have to check
you
that
will
out.
see.
Thank you.
I think you'll see something very similar to your example in
yeah.
a bunch of other examples. Anyway, just want to mention a good topic.
Yeah, I appreciate that.
Thanks. Bye-bye.
Great. Thank you.
If you're still here, I have a question too.
What's up?
Have you modeled this where you say, I'm going to stop after 15 tries every time and just see what happens?
I did try, simulating it on a computer. And one thing that happens is that, usually, you kind of go broke pretty fast. And sometimes you hit a winning streak early on and you get like a huge number of coins banked up. Like the best I saw was like several billion coins.
Wow.
And I went through, I don't know, several 100,000 turns, machines. I mean, now if you're doing this on a computer, once you have billions of coins, you really have to, do some kind of like normal approximation to the binomial or something like that, rather than make the computer do billions of simulations for just one round.
Right.
But I think I did it right. And eventually, even with billions of coins, eventually you just hit a losing streak. Eventually is a really long time.
Yeah, I would imagine the distribution of how many times you can go would be really weird.
Yeah, I mean, and there is this. The thing is that these slot machines are getting less and less biased in your favor. That's the problem. If they were just the same slight gain every time, then you could work up to having enough coins where the central limit theorem or whatever works in your favor, and you basically stay, just end up just always increasing. But that just doesn't work if that game keeps changing and that edge keeps getting more and more like a coin toss, because then it looks like a random walk. And we have this theorem that, in a fair random walk, like on the integers, you're guaranteed to hit 0. You're guaranteed to hit every number. You're guaranteed to hit every number infinitely often. So, So yeah, that's what's happening. It looks more and more like a zero bias, fair.
That makes sense. That's a very cool problem. Thank you so much.
Well, thank you, Dominic. Good to see you.